Hey, sleepers! Tonight, we're untangling the very fabric of the universe, pulling at the threads of time and light to see what holds them together. Imagine a beam of light traveling across a vast, dark ocean of stars, bending gently as it passes a sleeping sun. So before you get comfortable, take a moment to like the video and subscribe. I would love to know where you are joining us from tonight and what time it is in your corner of the world. So please leave a comment down below. So close your eyes, take a deep breath, and get ready to drift off as we explore the mind of Albert Einstein. Our story begins in a time before airplanes streaked across the sky, before the internet connected our thoughts, and before we understood that the stars were made of the same fire that warms our hearths. We begin in the quiet, cobblestone city of Ulm, in the Kingdom of Württemberg, which was then a part of the German Empire. It is the 14th of March, in the year 1879. The winter is fading, giving way to the first damp, gray hints of spring. The Danube River flows silently through the city, a constant moving presence that has watched generations come and go. In a modest apartment, a child is born. His name is Albert. When he arrives, the household is not filled with immediate relief, but with a quiet, creeping anxiety. The baby's head is large, unusually so. It is shaped in a slightly angular way that causes his grandmother to wring her hands and whisper her worries to the mother Pauline. They fear the child might be deformed, or perhaps that his mind will not develop as it should. But nature is patient. As the weeks turn into months, the shape of his head settles. The infant grows. He has dark hair and large, expressive eyes that seem to take in everything, yet give away very little. However, as Albert moves from infancy into toddlerhood, a new worry takes root. The other children in the neighborhood are noisy creatures. They shout, they mimic the sounds of the street, they babble to their parents. But Albert is silent. He watches. He observes the way the light hits the floor, the way the leaves move in the wind, but he does not speak. He is 2 years old, and he says nothing. He is 3 years old, and still the words do not come. His parents, Hermann and Pauline, are terrified. They consult a doctor, fearing that their son might be mute or have a developmental delay. The doctor tells them to wait, and so they wait. When the words finally do come, they do not arrive in a rush of babble. They arrive with a strange, methodical precision. Even as a young boy, Albert develops a ritual that he will keep for years. Before he speaks a sentence out loud, he whispers it softly to himself. He moves his lips, testing the rhythm of the phrase, checking the weight of the words, ensuring they are exactly right. Only when he is satisfied does he speak them aloud. It is our first glimpse into the machinery of his mind. It is a mind that refuses to rush. It is a mind that values silence and contemplation over the noise of immediate reaction. He is not slow. He is thorough. He is living in a world of his own pacing. There is a specific moment in his childhood, a single afternoon that will ripple through the rest of his life like a stone dropped in a still pond. Albert is 5 years old. He is lying in bed, perhaps feeling a bit under the weather. His father, Hermann, comes into the room. Herman is a businessman, a jovial man with a thick mustache, who works in the electrochemical industry. He wants to cheer up his son, so he reaches into his pocket and pulls out a small object. It is a magnetic compass. Albert reaches out and takes the cold metallic disc in his small hands. He looks at the face of it. There is a needle, trembling slightly, floating in its casing. Albert turns the compass. He spins it around. He tilts it. But no matter how he moves, the needle ignores him. It ignores the motion of his hand. It points steadily, relentlessly, toward the north. The boy is struck by a sensation that is almost physical. He feels a sudden cold shiver of wonder. Up until this moment, he understood the world through touch. You push a toy, and it moves. You throw a ball, and it flies. Contact causes action. But here, inside this little metal box, something else is happening. The needle is being guided by an invisible hand. It is reaching out across empty space, connecting to a force he cannot see, cannot hear, and cannot touch. That moment, lying in his bed in Munich, Albert realizes that there is a hidden layer to reality. There is a something behind the everything. That sense of awe, that deep, shivering mystery will become the fuel for his entire life. He will spend the next 70 years trying to understand the invisible forces that guide that needle, and the stars, and the passage of time itself. As he grows older, Albert enters the school system, and the wonder he felt with the compass collides with the rigid reality of German education. The Luitpold Gymnasium in Munich is a place of strict discipline. The teachers are not guides. They are authority figures. They value rote memorization. They want students to stand in rows, recite facts, and obey. They march around the classroom like drill sergeants. To a dreamer like Albert, this is a prison. He hates the mindless repetition. He hates the demand for obedience without understanding. He sits in the classroom, feeling the scratch of the wool uniform, smelling the chalk dust, and his mind drifts away. He looks out the window at the sky. He thinks about space. He thinks about light. His teachers mistake his boredom for stupidity. They mistake his silence for insolence. One teacher, in a moment of frustration, tells him, "Einstein, you will never amount to anything." The teacher says this because Albert's presence, his slight smirk, his distant eyes, undermines the teacher's authority. Albert is not a bad student, in truth. He is simply a student who refuses to learn in the way they want him to. But while he suffers in school, at home, he finds his true education. At the age of 12, a family friend, a medical student named Max Talmud, brings him a book. It is a textbook on Euclidean geometry. Albert opens the book, and it is as if a light is switched on in a dark room. He calls it his holy geometry book. Here, in these pages, there is no ambiguity. There is no, because I said so. There is only pure crystalline logic. One truth leads to another truth, building a staircase of reason that climbs higher and higher. Albert devours the book. He proves the theorems on his own, often finding new ways to solve them that the book doesn't even mention. He finds a deep, soothing comfort in the certainty of mathematics. In a world that is confusing and full of arbitrary rules, Math is safe. Math is true. By the age of 15, the myth that he is bad at math is already laughably false. While other teenagers are worrying about their social standing or playing games in the street, Albert has taught himself differential and integral calculus. These are the mathematical tools used to describe how things change, how a curve slopes, how water fills a vessel, how a planet orbits a star. He has mastered these complex concepts alone, sitting in his room, guided only by his curiosity. He doesn't do it for a grade. He does it because he wants to know the language of nature. However, life in Munich becomes unbearable for him. His father's business fails, and the family decides to move to Milan, Italy, to try again. They leave Albert behind in a boarding house to finish his schooling. He is 16, lonely, and miserable. The militaristic atmosphere of the school feels like a suffocating blanket. So, he makes a bold decision. He drafts a letter from a doctor claiming he has nervous exhaustion, and he quits. He leaves the school. He creates a plan to renounce his German citizenship so that he cannot be drafted into the army. He hates the idea of marching, of carrying a gun, of killing on command. He is a pacifist to his core. He travels to Italy to rejoin his family. Imagine the relief he must have felt crossing the Alps, leaving the gray, rigid discipline of Munich for the warmth and chaotic beauty of Italy. He spends months hiking through the Apennine Mountains, visiting art museums, and simply breathing. He is a dropout, a young man with no diploma and no clear future, but he is free. Eventually, his father tells him he must get serious. He needs a profession. Albert decides to apply to the Swiss Federal Polytechnic in Zurich. It is a prestigious institute, a place of serious science. He is still 2 years younger than the standard entrance age, but they allow him to take the exam. And here, we must pause to gently dismantle a famous legend. You have heard that Einstein failed this exam. Technically, yes, he did not pass, but let us look at the scores. He destroyed the math section. He obliterated the physics section. His understanding of these subjects was already at a university level. But the exam also required knowledge of French, literature, zoology, and botany. Albert had spent his time thinking about the cosmos, not memorizing the reproductive cycles of ferns or the grammar of French verbs. So he failed those sections. The director of the Polytechnic, a physicist himself, saw Albert's math scores and was stunned. He called the boy in. He told him, "You are brilliant, but you are not ready. Go to a high school in Aarau, Switzerland. Get your diploma. Learn a little French. Then come back to us." Albert follows this advice. He moves to Aarau. This year becomes a golden time for him. He lives with the family of one of the teachers, the Winteler family. The atmosphere is completely different from Munich. Here, students are encouraged to think for themselves. The Wintelers treat him like a son. He sits at their dinner table, engaging in long-spirited debates about politics and philosophy. He falls in what feels like love with a daughter, Marie Winteler. It is a sweet, innocent romance of letters and long walks. It is here, in Aarau, walking along the country roads, that Albert asks himself a question that will change the world. It is a thought experiment. He asks, what would happen if I could run alongside a beam of light? Imagine this with him. Close your eyes and picture a beam of light as a physical thing, like a long, glowing arrow flying through space. If you could run fast enough, if you could run at the speed of light, and you looked over at the light beam, what would you see? Would the light look frozen? Would it look like a wave that is standing still? To Albert, this seemed impossible. Light is movement. You cannot have frozen light. It was a paradox, a riddle. It lodged itself in his brain like a splinter, and he would spend the next decade trying to get it out. But there was another language Albert learned to speak during these quiet years. A language that existed without words, without formulas, and without the rigid authority of schoolmasters. It was a language made entirely of vibration and emotion. It was the language of music. To understand the rhythm of Albert's mind, we must first understand the rhythm of his home. His mother, Pauline, was a talented pianist. In the evenings, the Einstein household in Munich was not filled with idle chatter, but with the rich, rolling chords of Beethoven and the intricate, playful scales of Mozart. Pauline wanted her son to appreciate this world. She believed that music was a necessity for the soul, as vital as bread is for the body. So, when Albert was 6 years old, she placed a violin in his small hands. At first, the relationship between the boy and the instrument was not a happy one. The lessons were conducted by a strict instructor who believed in drills. Over and over again, Albert was forced to play scales: do, re, mi, fa, sol, up and down, rigid, mechanical. It felt exactly like the marching soldiers he hated in the streets of Munich. It felt like the classroom where he was told to memorize facts without understanding them. For a child who was already beginning to question the nature of time and space, this mindless repetition was a torment. He once threw a chair at his teacher in a fit of frustration. He hated the drill. He hated the lack of soul in the exercise. But then, when he was 13, something shifted. It was as if a cloud had moved away from the sun. He discovered the violin sonatas of Wolfgang Amadeus Mozart. Suddenly, the violin was not a tool for discipline. It became a key. Albert later said that he fell in love with Mozart's music because it did not feel composed. It did not feel like something a human being had made up. Beethoven's music, he thought, was dramatic and personal. It sounded like a man wrestling with his emotions. But Mozart? Mozart was different. Albert felt that Mozart's music was so pure, so logically perfect, and so harmoniously beautiful that it must have always existed in the universe. It felt like a law of nature, waiting to be discovered, just like gravity or electricity. It was not created. It was found. This idea resonated deeply with Albert's developing scientific mind. He was looking for the hidden structures of the universe, and in Mozart, he heard the soundtrack of those structures. From that moment on, he was never without his violin. He gave her a name. He called her Lina. It was an affectionate nickname, treating the wooden instrument like a dear friend or a beloved pet. Lina was not an expensive Stradivarius. She was a modest instrument, battered by travel and use, but to Albert, she was precious. She became his constant companion, his travel partner, and eventually his laboratory. You see, for Albert, music was not just a hobby. It was a method of thinking. It was a way to untangle the knots in his brain. Imagine him later in life, sitting in his study, staring at a page of equations. He is trying to understand how light travels or how gravity pulls. He hits a wall. The logic breaks down. The math becomes messy. He feels frustrated, his mind cramping up like a tired muscle. Instead of forcing the answer, instead of getting angry, Albert would stand up. He would walk over to the corner of the room where the case lay. He would undo the latches, click, click. He would lift Lina from her velvet bed. He would tighten the bow, apply a little rosin, and tuck the instrument under his chin. And then he would play. He would improvise. He would let his fingers run over the strings, feeling the vibration resonate through his jawbone, into his skull, and down into his chest. He would close his eyes and drift into the sound. He wasn't playing a specific song. He was playing his thoughts. There is a deep connection between music and physics that Albert understood intuitively. Both are about waves. Sound is a wave moving through the air, compressing and expanding the molecules. A low note is a long, slow wave, rolling like a heavy ocean swell. A high note is a fast, jittery wave, rippling like a pebble thrown in a pond. Harmony happens when these waves line up perfectly, when the peaks and valleys of the sound match each other. As Albert played, his mind would relax. The rigid walls of impossible would dissolve. He said that while he played, he would often think in images. He would see visual structures rising and falling with the melody. A complex problem in physics often requires a leap of imagination, a jump from what is known to what is unknown. Music provided the bridge for that jump. His eldest son, Hans Albert, later described this process. He said, whenever he felt that he had come to the end of the road or into a difficult situation in his work, he would take refuge in music. That would usually resolve all his difficulties. Albert would play for an hour, lost in a trance of notes, and then suddenly he would stop. He would lower the violin, a look of calm clarity on his face, and say, "There, now I've got it." He would put Lina away and return to his desk, the answer having arrived on the back of a melody. It is a beautiful thing to visualize. The man who revealed the curvature of space-time, standing in his socks in a cluttered room, playing a sweet, simple melody to unlock the secrets of the cosmos. It suggests that the universe is not just a machine of gears and levers, but a song, a symphony of light and gravity. Albert carried Lina everywhere. When he traveled to conferences, he didn't care about packing fancy suits, but he always packed his violin. He loved to play with others. He didn't care if they were professionals or amateurs. He once played quartets with the Queen of Belgium. Another time, he played with a group of neighbors. He loved the democracy of music. In a quartet, there is no boss. No one is giving orders. Everyone must listen to everyone else. You have to breathe together. You have to anticipate the other person's move. It is a perfect model of cooperation. There is a funny and charming story about his rhythm, however. Albert was a genius of time and physics. He knew that time could stretch and shrink. But in music, time is strict. You must keep the beat. Once, he was playing a quintet with the famous Juilliard String Quartet. They were playing Mozart. Albert was playing the second violin part. In the middle of a fast movement, Albert missed his entry. He came in too late. The music fell apart. The group stopped. The cellist looked at the world's greatest physicist and said, gently but firmly, "Albert, your problem is that you can't count." Albert laughed the loudest of anyone. He loved that. In the world of music, he wasn't the great Einstein. He was just a guy trying to keep up with the beat. But music was also his refuge in sorrow. We must remember that his life was lived against the backdrop of terrible wars and personal losses. When his mother was dying, Albert was devastated. He could not find words to express his grief. Words felt small and empty, so he played for her. In her final days, he would stand in the living room and play the music she had taught him to love. It was his way of holding her hand, his way of saying goodbye without saying a word. And later, when he was forced to flee Germany, when he watched the country of his birth descend into darkness, Lina was one of the few things he brought with him across the ocean to America. In his house in Princeton, on Wednesday nights, he would host chamber music sessions. People would gather outside his house, sitting on the sidewalk in the dark, just to listen to the faint, sweet sound of the professor's violin drifting through the open window. He had very specific tastes. He loved Bach and Mozart for their structure. He liked Schubert for his emotion. But he had a complicated relationship with Beethoven. He found Beethoven too aggressive, too turbulent. He said, Beethoven's music is personal and dramatic, but Mozart's music is cosmic. Albert didn't want drama. He wanted the stars. He wanted the eternal. There is a scientific concept called resonance. If you pluck a string on one violin, and there is another violin across the room, the matching string on the second violin will start to vibrate, even though you didn't touch it. The sound wave travels through the air and wakes up the sleeping string. Albert Einstein was like that second violin. He was tuned to the frequency of nature. When he played music, he was tuning himself, tightening the pegs of his mind until he resonated with the frequency of the universe. So, as we imagine him in those early years, before the fame, before the white hair, picture a young man with dark, curly hair, standing by a window in Switzerland. Outside, the Alps are rising in the distance, silent and white. Inside, there is the smell of old paper and pine resin. He is holding Lena. He closes his eyes. He takes a breath. He draws the bow across the string, a long, clear note that sustains in the quiet air. In that single note, there is physics. There is math. There is emotion. And there is the beginning of a journey that will change the world. He lowers the bow. He smiles to himself. He has found the rhythm he was looking for. Now, he is ready to go back to his books. This love for the hidden harmonies of the world would carry him through his next great challenge. After finally obtaining his high school diploma in Aarau, Albert felt ready. He returned to Zurich. These are his college years. He is a handsome young man now, with a shock of dark, wavy hair and eyes that sparkle with a mix of intelligence and mischief. He is not the most diligent student in the traditional sense. He hates the boring lectures. He skips classes constantly. Instead of sitting in the lecture hall, he spends his time in the cafes of Zurich, drinking coffee, smoking a pipe, and reading the absolute latest papers in theoretical physics. He reads works that his professors haven't even caught up with yet. He makes friends who will be crucial to his journey. There is Marcel Grossmann, a brilliant mathematician who is organized and diligent. Everything Albert is not. Marcel takes meticulous notes in class, and Albert borrows them to pass his exams. Without you, Albert tells him, I would be lost. And there is Mileva Marek. She is the only woman in their physics program. She is serious, dark-haired, and fiercely intelligent. She shares Albert's passion for science. They fall in love over textbooks and equations. They write letters to each other filled with physics problems and terms of endearment. She becomes his sounding board, the person he bounces his wildest ideas off of. When Albert graduates in 1900, he expects to be welcomed into the academic world. He imagines a junior professorship, a lab, a life of research. But his reputation as a rebel has preceded him. His professors remember him as the arrogant student who skipped class. They do not offer him a job. He applies to universities across Europe. He sends polite letters, enclosing his resume. He receives silence. He reaches a point of desperation. He writes to a professor in Leipzig, essentially begging for a position. He even offers to work for free. Still, nothing. He is 22 years old. He is unemployed. He is hungry. He tries to make money by tutoring high school students in math, but the pay is poor and the work is unsteady. He feels like a failure. He writes to his family, lamenting that perhaps it would have been better if he had never been born. It is the lowest point of his life. The genius is adrift. Then the universe intervenes. His friend Marcel Grossmann speaks to his father, and his father speaks to the director of the Swiss Patent Office in Bern. An interview is arranged. Albert travels to Bern. He impresses the director, not with his knowledge of patent law, but with his ability to understand complex mechanical drawings instantly. He gets the job. He is hired as a technical expert, third class. It is a lowly government position. He sits in a small office on the third floor of the building. The room smells of stale tobacco, ink, and paper. Outside the window, he can see the rooftops of Bern, and in the distance, the majestic, snow-capped peaks of the Alps. His job is to read applications for new inventions. He looks at designs for gravel sorters, for new types of gears, for electric typewriters. He has to decide. Is this new? Will it work? Most people would find this job tedious. For Albert, it is a miracle. He finds that his mind is so sharp, so visual, that he can finish a whole day's work in just 3 or 4 hours. He does not tell his boss this, of course. He keeps his head down, but in the drawer of his desk, hidden underneath the patent files, he keeps his own papers. He calls this desk his worldly monastery. It is a safe harbor. Here, No one cares about his academic record. No one cares about his bad attitude in class. He is left alone with his thoughts. And what thoughts they are. In the quiet moments between checking a design for a new refrigerator and a new kind of clock, Albert stares into the particles of dust dancing in the sunbeams. He thinks about the nature of time. Bern is a city of clocks. There is the famous Zittglogg clock tower, which has marked time for centuries. The trains in Switzerland run on precise schedules. The coordination of time, making sure the clock in Bern strikes noon at the exact same moment as the clock in Zurich, is a major technological problem of the day. Albert thinks about this. What does it mean for two things to happen at the same time? However, before we step into the blinding light of that miracle year, we must pause in the shadows. To understand the intensity with which Albert threw himself into his work, we have to look at the silence that was growing in his heart. History often paints geniuses as figures made of marble, cold, perfect, and detached. But Albert was a man of deep, messy, human emotions. And in the years leading up to 1905, he and Mileva were guarding a secret that would remain hidden for almost a century. It began while they were still students in Zurich. Their romance was a bohemian one. They were two physicists against the world, reading books together, drinking coffee, and dreaming of a life of the mind. They were young, they were in love, and they were unmarried. In the strict, conservative society of Switzerland in 1901, this was already a difficult position. But then, Mileva discovered she was pregnant. For a young man with no job, no money, and a family who disapproved of his relationship, this was a terrifying development. But the letters between Albert and Mileva from this time are not filled with fear. They are filled with a secret, tender code. They wrote to each other constantly. They didn't speak of a baby. They spoke of their future child with playful nicknames. If it was a boy, he would be Lieserl. If it was a girl, she would be Lieserl. As the pregnancy progressed, Mileva had to make a heartbreaking choice. She could not stay in Zurich. The scandal would have ruined Albert's chances of getting a job, and his career was their only hope for a future. So, she packed her bags. She returned to her family's home in the Vojvodina region, in what is now Serbia. It was a long, cold journey away from the man she loved. Albert stayed behind in Switzerland, hunting for work, trying to find that elusive job at the patent office. This period of separation is documented in a series of letters that were found in an old shoe box by Einstein's granddaughter only in the 1980s. Until that box was opened, the world had no idea this chapter of his life existed. In these letters, we see a different Albert. He is not the sage of science. He is a young, anxious father-to-be. He writes to Mileva about his scientific ideas, yes. He talks about the motion of bodies and the nature of force. But in the next sentence, he asks about her health. He asks about our little one. He sends her sketches of his room. He tries to be there, across the miles, through the ink on the page. In January 1902, while the winter snows were deep in Serbia, the news came. Mileva had given birth to a little girl. They named her Lieserl. Albert was in Bern when the letter arrived. His excitement leaps off the page of his reply. He wrote, "Is she healthy? Does she cry properly? What are her eyes like? Which one of us does she resemble more?" He was desperate to visualize this new life. He wrote that he loved her already, even though he did not know her yet. He asked Mileva to draw a picture of her. He wanted to know everything. But here, the story enters a thick, gray fog. Albert never went to Serbia to see the baby. He couldn't. He had just started his job at the patent office. He had no money for the train ticket, and he could not risk losing his position by taking leave so soon. He was trapped by his poverty and his ambition. Mileva eventually returned to Switzerland to marry Albert. They had a quiet civil ceremony in Bern, but she came alone. Lieserl did not come with her. The child stayed behind in Serbia, cared for by Mileva's relatives, friends. We can only imagine the conversations that happened between Albert and Mileva in their small apartment in Bern. The grief of a mother leaving her child. The pragmatic, painful decision of a father who felt he could not support illegitimate child while trying to become a respectable civil servant. It was a decision made of fear and necessity, a decision that must have hung over their marriage like a heavy, damp curtain. For a year, Lieserl existed in their letters. Mileva would get updates from home. But then, in September 1903, the news turned dark. Lieserl had contracted scarlet fever. It was a dangerous disease in a time before antibiotics. Albert wrote a letter asking, "How is the child registered? We must take precautions so that problems don't arise for her later." He was worried, but he was also distant. He was a father who had never held his daughter, never seen her smile, never felt the weight of her in his arms. She was an abstract concept to him, a Lieserl made of words and worry, not flesh and blood. And then the mentions of her stop. Lieserl disappears from the historical record. Did she die from the fever? Did she survive and get adopted by another family? Historians have searched through Serbian church records and graveyards, looking for a death certificate or an adoption paper. They have found nothing definitive. She simply vanished. It is likely that she passed away in childhood, or perhaps was raised by relatives under a different name, never knowing that her father was the man who was rearranging the universe. Albert Einstein, the man who would eventually unlock the secrets of the atom, who would become the most famous human being on the planet, had a daughter he never met. This silence is profound. Albert never spoke of her again publicly. He never told his later children, Hans Albert and Edward, that they had an older sister. He buried this memory deep inside him. Why do we dwell on this sad story tonight? Because it gives us a window into the mind of the man in the patent office. We often wonder how someone could focus so intensely, how they could produce so much genius in such a short time. Perhaps the work was not just a passion. Perhaps it was a refuge. Imagine Albert in 1904 and 1905. He is living with a secret tragedy. He has failed as a father in the most traditional sense. He has lost a child to the distance and the silence. The real world, the world of money, of social rules, of sickness and death, is painful. It is messy. It is uncontrollable. But in his desk drawer, on those sheets of paper where he scratches out his equations, the world is perfect. In the world of physics, there is no sickness. There is no scarlet fever. There is only logic, symmetry, and order. If an equation doesn't balance, you can fix it. If a theory is wrong, you can correct it. The atoms obey the rules. Light follows the path it is given. It is very possible that the Annus Mirabilis, the miracle year, was fueled by a need to escape the heartbreak of the real world. He poured all his energy, all his emotion, and all his need for order into the one place where he had total control, the laws of the universe. He built a cathedral of logic to shelter himself from the rain of human sorrow. Lieserl became a ghost in the machine. She was the shadow that made the light of his intellect shine even brighter. She reminds us that even the greatest minds are attached to human hearts, and those hearts can break. The man who sat at that desk in Bern was not just a brain in a jar. He was a young man carrying a heavy, invisible burden, seeking solace in the stars. So, as we prepare to look at the papers he wrote, let us remember that they were written by a man who knew the fragility of life. He was looking for something eternal, something that could never be taken away, something that would last forever. And he found it. And so, with his heart quieted by work and his mind sharpened by solitude, we arrive at the year that changed everything. Let us drift now to the year 1905, the miracle year. Albert is 26. He is poor, unknown, and working as a clerk. He is married to Mileva now, and they have a baby son, Hans Albert. In the evenings, he rocks the baby's cradle with one hand and writes equations with the other. In this single year, he produces 4 scientific papers. Any one of these papers would have been enough to secure his place in history. Together, they are an explosion of intellect that sweeps away the old world. Let us walk through these ideas gently, one by one. The first paper concerns light. For a century, scientists believed light was a wave, rippling through space like waves across a lake. It was a beautiful, continuous motion. But there were problems with this theory. Albert looks at the data and suggests something that sounds almost like heresy. He says, yes, light acts like a wave, but it also acts like a particle. He proposes that light is made of tiny individual packets of energy. He calls them quanta. Today, we call them photons. Imagine standing in a warm summer rain. You feel the water as a wetness, but you also feel the individual taps of the drops against your skin. Albert says light is like that ring. It is grainy. When these light grains hit a metal surface, they knock electrons loose, like billiard balls colliding. This is the photoelectric effect. It explains how we can turn light into electricity. Every time you walk through an automatic door at the grocery store, or look at a solar panel soaking up the sun, you are seeing Albert's idea in action. He showed us that the smooth beam of light is actually a stream of tiny, energetic bullets. The second paper is about atoms. In 1905, believe it or not, many serious scientists still thought atoms were just a convenient fiction, a way to do math, but not real physical objects. Albert looks at a cup of tea. He imagines a tiny grain of pollen floating in it. Under a microscope, That grain of pollen dances. It jitters. It moves left, right, up, down, trembling as if it is cold. This is called Brownian motion. For decades, it was a mystery. Is the pollen alive? Is it electricity? Albert uses pure mathematics to show that the pollen is dancing because it is being hit. It is being bombarded by millions of invisible water molecules. Imagine a giant inflatable ball at a rock concert. The crowd is pushing it, punching it. From a helicopter, you can't see the individual people in the crowd, but you can see the ball moving erratically. You know the people are there because the ball is moving. Albert calculates the size and speed of these invisible molecules based on the dance of the pollen. He proves once and for all that matter is made of atoms. He makes the invisible visible. The third paper is the one that bends our minds. Special relativity. He returns to his old question. What if I run alongside a beam of light? He realizes that the universe has a speed limit. The speed of light is constant. It is 299,792,458 meters per second. It never changes. Whether you are standing still or flying in a rocket ship, if you measure the speed of light, it is always the same. But how can this be? If I throw a ball while running, the ball moves faster than if I throw it while standing still. Velocities usually add up, but not for light. To make the speed of light constant, Albert realizes that the rest of the universe must be flexible. Space and time are not rigid stages. They are like rubber. They can stretch and squeeze. Imagine you are on a train moving very, very fast. You have a special clock made of 2 mirrors with a beam of light bouncing between them. Tick, tock, up and down. To you on the train, the light goes straight up and straight down. But to your friend standing on the platform, watching the train zoom by, the light has to travel diagonally to keep up with the mirrors. Diagonal lines are longer than vertical lines. This means the light has to travel a longer distance. But the speed of light cannot change. So, if the distance is longer and the speed is the same, the time it takes must be longer. This leads to a conclusion that feels like a dream. Time slows down for moving objects. The faster you move, the slower your time ticks. If you could travel in a spaceship at 99% of the speed of light to a distant star and come back, you might have aged only 1 year. But on Earth, 10 years might have passed. Your friends would be older, gray-haired, while you are still young. Albert shows us that time is personal. My time is not your time. We each carry our own clock, and it ticks to the rhythm of our motion. The fourth paper is a short addendum to the third. It contains an equation that even a child knows today. E equals mc. Energy, E, equals mass meter times the speed of light, c squared. In this simple equation, Albert reveals a secret about the stuff of the world. He tells us that mass and energy are the same thing, just wearing different clothes. A rock, a book, a cup of coffee, these are just forms of trapped, frozen energy. And because the speed of light is such a huge number, and squaring it makes it unimaginably huge, the equation tells us that a tiny amount of mass holds a titanic amount of energy. Imagine a single paperclip. It sits on your desk, innocent and small. But Albert tells us that if you could unlock all the energy holding that paperclip together, it could power a city. It could boil a lake. The matter we touch every day is shimmering with potential power. It is a profound, almost spiritual realization. The physical world is made of light and energy, condensed and slowed down. The year 1905 ends. Albert sends his papers to the Annalen der Physik, the leading physics journal. He expects. Well, he doesn't know what to expect. Perhaps silence. Perhaps ridicule. But slowly, the letters start to arrive. The great physicists of the world, Max Planck, Marie Curie, begin to read his work. They are baffled, then intrigued, then convinced. The clerk in the patent office has seen something they all missed. But Albert is not satisfied. His theory of special relativity has a hole in it. It only works for things moving in straight lines at constant speeds. It doesn't explain the most common force in our lives, gravity. What is gravity? Isaac Newton, the giant of physics, said gravity is a force. The earth pulls the apple. The sun pulls the earth. But how? Does the sun have invisible ropes? Does it whisper to the earth? Newton didn't know. He just calculated the effects. Albert wants to know how. He spends the next 10 years obsessed with this problem. It is a decade of intense struggle. He leaves the patent office and becomes a professor in Zurich, then Prague, then back to Zurich, and finally he is lured to Berlin. He is famous now within the scientific community, but his personal life is fraying. His obsession with gravity isolates him. His marriage to Mileva collapses. They separate. He is alone in Berlin, living in a bachelor apartment, eating poorly, often forgetting to sleep. He develops stomach trouble. He is exhausted. But he cannot stop. He has a breakthrough. He calls it the happiest thought of my life. He imagines a man falling off a roof. Albert's experiments often involve people in perilous situations, but in the safety of the mind, he realizes that when you are falling, you don't feel gravity. You are weightless. If you took your keys out of your pocket while falling, they would float right next to your face. He realizes that gravity is not a pulling force. It is a curvature. Imagine a soft, comfortable mattress. It is flat. Now place a heavy bowling ball in the center. The ball sinks into the mattress, creating a dip, a curve. Now, take a marble and roll it across the mattress. The marble tries to go straight, but when it hits the dip, it curves. It circles around the bowling ball. It isn't being pulled by a rope. It is just following the shape of the mattress. Albert says space and time are like that mattress. He calls it space-time. The sun is a heavy weight that bends the fabric of the universe. The earth is a marble rolling along that curve. We are not held to the ground by a force. We are being pushed down by the curvature of time itself. He publishes the theory of general relativity in 1915. It is a masterpiece. It is arguably the greatest intellectual achievement of a single human mind. He has replaced Newton's universe with a geometric, flexible, dynamic cosmos. But again, it is just a theory. It needs proof. Albert makes a prediction. He says, "If I am right, light should bend. If a star is sitting behind the sun, the light from that star should curve around the sun's gravity well and be visible to us. It should be shifted from its true position. The only way to see a star near the sun is during a total solar eclipse when the moon blocks the sun's glare. The world is at war. World War I makes travel impossible. Albert has to wait. He sits in Berlin, malnourished and anxious, while the nations of Europe tear each other apart. Finally, in 1918, the war ends. In 1919, a British astronomer named Arthur Eddington decides to test Albert's theory. It is a poetic moment. A British scientist testing the theory of a German scientist, healing the wounds of war through the shared pursuit of truth. Eddington leads an expedition to the island of Principe, off the coast of West Africa. He hauls massive telescopes into the jungle. He battles mosquitoes and heat. On the day of the eclipse, May 29, 1919, a storm rolls in. Rain lashes the equipment. It seems the experiment is doomed. But at the last moment, the clouds part. The sun, now a black hole in the sky, surrounded by a corona of fire, appears. Eddington snaps his photos. He returns to England to measure the plates. The results are clear. The stars are not where they are supposed to be. They have moved. Their light has been bent by the sun's gravity, exactly as Albert predicted. On November 7, 1919, the results are announced in London. The headline of the London Times reads, "Revolution in Science. New Theory of the Universe. Newtonian Ideas Overthrown." However, just as the world was crowning him the king of science, Albert was quietly wrestling with a demon of his own making. It is a story that brings a great sense of comfort to anyone who has ever made a mistake. It reminds us that being a genius does not mean being perfect. It means being brave enough to correct yourself. After he finished his general theory of relativity, Albert felt a sense of immense satisfaction. He had explained gravity. He had explained the motion of the planets. But Albert was not a man to stop at the edge of the solar system. He wanted to apply his new equations to the biggest object of all, the entire universe. He wanted to write an equation that described the shape and fate of the cosmos itself. But when he sat down in Berlin in 1917 to do the math, something strange happened. His own equations, the beautiful, elegant formulas he had just created, gave him an answer he hated. They told him that the universe was unstable. The math said that because all objects have gravity, and gravity pulls things together, the universe should be collapsing inward, crushing itself into a ball. Or, if it had enough energy, it should be flying apart, expanding outward forever. The math said the universe was moving. It was dynamic. It was alive. But Albert couldn't accept this. Like almost every scientist before him, going back to Aristotle, he believed deep in his bones that the universe was static. He believed it was eternal, unchanging, and still. The stars were where they were, and they had always been there, fixed in the velvet dark, like diamonds glued to a ceiling. The idea of a universe that was stretching or shrinking felt wrong to him. It felt chaotic. It felt ugly. So, in a moment of stubbornness, Albert decided to fight his own math. He took his pen and added a new term to his equation. He called it the cosmological constant, represented by the Greek letter lambda. Think of it like a fudge factor. It was a mathematical scaffold. He invented an invisible energy that pushed outward against gravity. He balanced the pulling of gravity with the pushing of this constant, freezing the universe in place. It was like balancing a pencil on its tip, artificially perfect, held in place by an invisible hand. With this addition, the universe became safe again. It became still. For more than a decade, Albert slept soundly, believing he had described an eternal, unchanging cosmos. But while Albert was writing equations in Europe, a lawyer-turned astronomer named Edwin Hubble was sitting on a cold mountain peak in California. Hubble was working at the Mount Wilson Observatory. He was looking through the Hooker telescope, which was then the largest eye on Earth. It was a massive machine, a cannon of glass and steel pointed at the night. Night after night, shivering in the cold mountain air, Hubble took photographs of distant fuzzy patches of light called nebulae. He analyzed the light coming from them. He noticed something known as redshift. When an ambulance drives away from you, the siren sounds lower and deeper. Light does the same thing. When an object moves away from you very fast, its light stretches out and looks redder. Hubble found that almost all the galaxies he saw were red. They were rushing away from us. And the farther away they were, the faster they were running. The universe was not standing still. It was exploding outward. It was expanding like a balloon being inflated. In 1931, Albert traveled to California to see this for himself. Picture the scene. The world's greatest theorist meeting the world's greatest observer. They drove up the winding, dusty road to the observatory. Albert, with his wild hair and baggy trousers, walked into the dome. The massive telescope loomed above them, smelling of oil and cold iron. Hubble invited Albert to look through the eyepiece, or, more accurately, to examine the photographic plates he had taken. Albert looked. He saw the spectral lines shifted to the red. He saw the undeniable proof of the expanding universe. The math he had tried to suppress was actually the reality of nature. In that quiet dome, surrounded by the silence of the mountains, Albert did something that many powerful men cannot do. He changed his mind. He realized that if he had just trusted his original equations, if he hadn't been so afraid of a moving universe, he could have predicted the expansion of the cosmos 10 years before Hubble saw it. He could have made the greatest prediction in the history of human thought. Instead, his bias had held him back. He turned to Hubble and the other astronomers. He didn't make excuses. He didn't argue. He smiled. He announced that the cosmological constant was unnecessary. He later famously called it his greatest blunder. He took his pen and crossed the lambda out of his equation. He accepted the universe as it was, not as he wanted it to be. There is a profound lesson here for us as we drift off to sleep. We often try to force the world to be stable. We try to control things to keep them fixed and unchanging, because change is scary. We build our own cosmological constants to hold everything in place. But the universe is not static. It is expanding. It is moving. Life is a river, not a rock. Albert's Blunder teaches us that it is okay to be wrong. In fact, being wrong is part of the process of finding the truth. Even the mind that understood the speed of light could be blinded by its own beliefs. But in the end, he was humble enough to look through the telescope and say, "I see." And here is a final ironic whisper from the future. Decades after Albert died, in the late 1990s, scientists discovered that the universe is not just expanding, but accelerating. To explain this, they had to bring back Albert's cosmological constant. It turns out his mistake might actually be the mysterious dark energy that fills the vacuum of space. Even when he was wrong, he was somehow right. In a heartbeat, Albert Einstein is no longer just a physicist. He is a global icon. The world, traumatized by the horrors of the trenches and the mustard gas of World War I, is desperate for something pure, something that transcends nations. They find it in Einstein. He becomes the face of genius. He is mobbed wherever he goes. Reporters follow him to the grocery store. They ask him about God, about politics, about the future of the human race. He looks the part. His hair is becoming the wild white halo we all recognize. He stops wearing socks because he finds them unnecessary. He has a playful, self-deprecating humor. When Charlie Chaplin invites him to a movie premiere, the crowds go wild. Chaplin whispers to him, "They cheer me because they all understand me, and they cheer you because no one understands you." Albert laughs. He travels the world. He goes to America, to Japan, to Palestine. He plays his violin, which he calls Lina. Music is his escape. He loves Mozart. He says that Mozart's music is so pure that it feels like it was plucked from the universe itself. When he is stuck on a physics problem, he plays the violin until the solution floats into his mind. In 1921, he receives the Nobel Prize. Ironically, the committee is too afraid to give it to him for relativity. It is still considered too wild. So they award it for the photoelectric effect. It doesn't matter. He has already won the admiration of history. However, while the world celebrated him as the man of the stars, the man who measured the bending of light and the stretching of time, Albert remained deeply connected to the ground. He was not just a dreamer floating in the clouds of theory. He was a man who cared about the practical sufferings of ordinary people. He believed that science should not just explain the universe. It should serve humanity. And in the mid-1920s, in the bustling, noisy city of Berlin, this belief led him to an invention that had nothing to do with relativity and everything to do with keeping milk cold. It began on a simple morning in 1926. Albert was sitting in his kitchen, reading the newspaper over his breakfast. He turned the page and saw a tragic headline. It was a story about a family in Berlin, parents and children, who had died in their sleep. The cause was not a fire or a crime. It was their refrigerator. In those days, refrigerators were not the safe, humming white boxes we have today. They were mechanical beasts that used toxic gases like methyl chloride, ammonia, and sulfur dioxide to keep food cold. These gases were pumped through the system by mechanical compressors with moving parts. If a seal broke or a valve leaked, which happened often, as the technology was still crude, the poisonous gas would escape. It was odorless and colorless. The family never woke up. Albert was horrified. He put down the newspaper, deeply shaken. Most people would have read the story, felt a moment of sadness, and turned the page. But Albert's mind didn't work that way. He saw a problem that needed a solution. He thought it was unacceptable that a machine designed to preserve life by keeping food fresh could end up taking life instead. He turned to a young friend of his, a brilliant Hungarian physicist named Leo Szilard. Szilard was one of the few people who could keep up with Albert's intellect. He was sharp, energetic, and practical. Albert showed him the newspaper and said, "We must do something about this." And so, the Einstein-Szilard partnership began. It was not a partnership of blackboard equations and chalk dust. It was a partnership of tinkering. They met in their spare time, rolling up their sleeves to act as engineers. They approached the problem with the elegance of physicists. They asked, "Why do refrigerators break?" The answer was friction. They broke because they had moving parts, pistons, pumps, motors. Moving parts wear out, seals crack, leaks happen. Albert posed a radical question. Is it possible to build a refrigerator with no moving parts at all? It sounds like a riddle. How can you pump coolant without a pump? How can you move fluid without a motor? They spent months working on the design. They sketched. They argued. They filed patents. Eventually, they would hold more than 45 patents for their cooling systems. The solution they found was a masterpiece of applied physics. They used a combination of butane, ammonia, and water, utilizing the concept of electromagnetism. Remember the compass Albert held when he was 5 years old? The needle that moved by an invisible force? He used that same force now. They designed a pump that used a magnetic field to move a liquid metal, which in turn acted as a piston to compress the gas. There were no gears, no rotating belts, no friction. The only thing moving was the liquid itself, guided by the silent hand of magnetism. Because there were no moving parts, there were no seals to break, no toxic leaks. And perhaps most beautifully, the machine was completely silent. It didn't hum or rattle. It just stood there, a silent guardian of the kitchen, doing its work without complaint. They built a prototype. It worked. It was safe. They even sold the patent to the Swedish company Electrolux for a tidy sum of money, which Albert, generous as always, largely shared with Szilard, who had less income. You might be wondering, if they invented a perfect, safe, silent refrigerator, why don't I have one in my kitchen right now? The answer is a twist of fate. Just as they were perfecting their design, a new chemical was invented in America. It was called Freon. Freon was non-toxic, or so they thought at the time. We later learned it was bad for the ozone layer, but that is a different story. Freon made the traditional mechanical compressors safe enough for home use. The big companies preferred the mechanical design because it was cheaper to mass produce than Einstein's elegant magnetic pump. So the Einstein refrigerator was shelved. It became a footnote in history. But this story matters. It matters because it shows us the heart of the genius. It would have been easy for Albert to stay in his study, thinking about the curvature of the universe, ignoring the mundane tragedy of a broken appliance. But he didn't. He saw a danger to his fellow humans, and he felt a moral obligation to use his brain to fix it. He applied the same intellect that measured the galaxy to the task of saving a single family in their home. It shows us that for Albert, there was no hierarchy in science. There was only the beautiful challenge of making the world a little more understandable and a little safer. But science does not stand still. In the 1920s, a new group of physicists, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, begin to uncover the laws of the subatomic world. This is quantum mechanics. They discover that the world of the atom is not like the world of the stars. It is chaotic. It is fuzzy. They find that you cannot know where an electron is and how fast it is going at the same time. The more you know about one, the less you know about the other. They say that events at the atomic level are random. They are governed by probability. Albert hates this. He cannot accept it. He believes deeply that the universe is a place of cause and effect. He believes that if you have enough information, you can predict the future perfectly. He engages in a great debate with Niels Bohr. They meet at conferences, often at the Hotel Metropole in Brussels. They sit at breakfast, arguing over coffee. Albert invents brilliant puzzles to try to prove that quantum mechanics is wrong. Bohr spends all night thinking and comes back the next morning with the solution. Albert famously says, "God does not play dice with the universe." He believes in a God of order, the God of the philosopher Spinoza, a God who reveals himself in the lawful harmony of the world, not in the roll of a die. Or, exasperated but affectionate, replies, "Einstein, stop telling God what to do." History eventually proves Bohr right. The universe is, at its heart, probabilistic, but Albert's stubbornness is valuable. By challenging the theory, he forces the quantum physicists to refine their ideas. He sharpens the very sword that defeats him. As the 1930s dawn, a shadow falls over Europe. The Nazis take power in Germany. Albert represents everything they hate. He is Jewish, he is a pacifist, he is an intellectual, and he is a citizen of the world. His books are burned. His property is seized. He realizes he can no longer live in the country of his birth. In 1933, he sails for America. He never sets foot in Germany again. He accepts a position at the Institute for Advanced Study in Princeton, New Jersey. Princeton becomes his haven. Imagine the scene: a quiet American college town, lined with oak trees and red brick buildings. And there, walking down Mercer Street, is the most famous mind in history. He wears baggy pants held up by a rope. He licks an ice cream cone. He helps the neighborhood children with their long division. He is safe, but he is sad. He watches from afar as Europe descends into the nightmare of World War II. In 1939, the nightmare gets closer. Physicists discover that the atom can be split. The equation E equals mc is no longer just a theory. It is a recipe for a bomb. A colleague, Leo Szilard, comes to Albert. He tells him that the Nazis might be building a nuclear weapon. Albert is a pacifist. He hates war. But the thought of Hitler with an atomic bomb is unbearable. He sits at a wooden table at a vacation cottage on Long Island, wearing his undershirt, and signs a letter to President Franklin D. Roosevelt. It is a cautious letter, warning of the danger and suggesting that America must research this technology. That signature sets the Manhattan Project in motion. But Albert is not part of it. The FBI considers him a security risk. He is too left-wing, too uncontrollable. He stays in Princeton while others build the gadget. When the bombs fall on Hiroshima and Nagasaki in 1945, Albert is devastated. He hears the news on the radio. He puts his head in his hands and whispers, "Woe is me." He feels he has opened a box that can never be closed. He spends the last 10 years of his life campaigning for peace, for a world government that can control these weapons. He says, "I know not with what weapons World War III will be fought, but World War IV will be fought with sticks and stones." But amidst the heavy weight of politics and the shadow of the mushroom cloud, Albert never lost his spark. He refused to become a stiff marble statue of the great scientist. He remained, until the very end, a man with a mischievous sense of humor and a deep distaste for pomp and circumstance. And there is one moment, captured in a split second of silver and light, that proves this better than any biography. You have seen this image. It is perhaps the most famous photograph of a scientist ever taken. It appears on T-shirts, on coffee mugs, and on posters in dorm rooms around the world. In the photo, Albert is sitting in the back of a car. His white hair is wild, his eyes are wide, and he is sticking his tongue out at the camera. It looks like a moment of pure, childish silliness. But the story behind it is a story of exhaustion, rebellion, and a refusal to play the game. The date was March 14, 1951. It was Albert's 72nd birthday. By this point in his life, he was not just a physicist. He was a global monument. People treated him like a saint or a wizard. That evening, his friends and colleagues had thrown him a celebration at the Princeton Club. It was a long night. There were speeches praising his genius. There were toasts. There were endless handshakes. Albert hated this kind of fuss. He once said, "The cult of individuals is always, in my view, unjustified." He didn't want to be worshipped. He just wanted to work. As the party ended, Albert was exhausted. He was an old man, and his face hurt from hours of polite smiling. He walked out of the club, flanked by his friends, Dr. Frank Adelot and his wife Marie. They squeezed into the back seat of a dark limousine. Albert sat between them, bundled up in his heavy coat. He just wanted to go home. He wanted silence. But the world would not let him go. Outside the club, a pack of press photographers was waiting. They swarmed the car like moths around a street lamp. The flashbulbs popped, pop, 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 blinding him in the darkness. They shouted at him, "Professor, Professor, one more picture. Give us a smile, Professor." Just one smile for the birthday. Albert had smiled enough. He had played the role of the kindly genius all night. He was done. He wanted to show them that he was not a performing seal. He wanted to break the facade. A photographer named Arthur Sass pushed his camera right up to the open window of the car. "Smile, Professor," he yelled. In a split-second reaction, a moment of pure defiance, Albert didn't smile. He opened his eyes wide and stuck his tongue out as far as it would go. It was a gesture of, "Leave me alone." It was a gesture of, "I am human, not a god." It happened so fast that most of the photographers missed it. They were winding their film or looking away. But Arthur Sass clicked the shutter. At first, the editors at the news agency didn't want to publish the photo. They thought it was undignified. They thought it made the great Einstein look foolish. They were afraid it would tarnish the reputation of the Nobel Prize winner. But when Albert saw the photo, he didn't feel embarrassed. He laughed. He loved it. He loved it because it was honest. It stripped away the reverence and showed the trickster underneath. He loved it so much that he ordered 9 copies for himself. He took a pair of scissors and cropped the photo, cutting out his friends on either side, so it was just his face, the wild hair, and the tongue. He turned it into a greeting card. He sent it to his friends. On one copy, he wrote a message to a journalist friend. "This gesture you will like, because it is aimed at all of humanity." A civilian can afford to do what a diplomat would not dare. That photo became his legacy as much as E equals MC. It serves as a gentle reminder to us all. Even when you are carrying the weight of the universe on your shoulders, even when you are rewriting the laws of time and space, you must never take yourself too seriously. You must never let the world turn you into stone. It is a comforting image to hold in your mind. The old man in the back of the car, tired but free, sticking his tongue out at the expectations of the world. His final years are quiet. He lives in a small house with his stepdaughter and his secretary. He works on a new theory, a unified field theory. He wants to write one single equation that explains everything from the tiny electron to the massive galaxy. He wants to combine gravity and electricity. He sits in his study, scribbling symbols, searching for the ultimate pattern. He never finds it, but there is a nobility in the search. He is like an old sailor, still looking for one last island, never giving up on the horizon. On April 17, 1955, Albert experiences a sharp pain in his chest. It is an aneurysm, a blood vessel bursting near his heart. He is taken to the hospital. The doctors want to operate. They say they might be able to save him. Albert looks at them. He is 76 years old. He is tired. He says, "I want to go when I want. It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly." He lies in the hospital bed. He is calm. He speaks a few words in German to the night nurse, but she does not understand German, and so his last words are lost to history. In the early morning of April 18, 1955, the breathing stops. The man who explained time has run out of it. But the story has one last strange chapter. A pathologist named Thomas Harvey performs the autopsy. Without asking the family, he removes Albert's brain. He puts it in a jar of formaldehyde. He thinks, "This is the brain that saw the curvature of space. I must keep it." He drives away with the brain in the trunk of his car. For decades, the brain sits in jars, sometimes in a cider box, under a beer cooler in Kansas. It is a grotesque, weird journey. But eventually, scientists examine it. They find that the brain is not huge. It is normal-sized. But the parietal lobe, the part of the brain that handles 3D visualization and math, is 15% wider than average. It is missing a groove called the Sylvian fissure, which usually separates parts of the brain. Without this groove, the neurons can connect more easily. His brain was physically wired to see the universe as a connected whole. Yet, looking at the cells does not explain the man. It does not explain the humor, the kindness, the stubbornness, or the violin playing. It does not explain the feeling of awe he felt when he held that compass at age 5. Albert Einstein taught us that we are small, but our minds are vast. He taught us that the solid ground beneath our feet is actually a curving wave in the ocean of space. He taught us that time is a river that slows and speeds up. He showed us that we are made of stardust and energy. So tonight, as you drift toward sleep, remember his lesson. You are not just a person in a bed. You are a collection of atoms that have existed since the Big Bang. You are resting in the gentle curve of Earth's gravity. You are traveling through space at thousands of miles an hour, yet you feel still. The universe is holding you. So close your eyes, take a deep breath, and get ready to drift off as we explore the dreams that wait for you in the curvature of sleep. Good night.